Hello everyone. Oh, I can see it build up. I'll try to keep this relatively short because I know we are all rushing to go to the concrete mixer. So just to give you a little bit of background about myself, I just started as an assistant professor at the University of Miami. I work with Pranoy Soreneni on my PhD, and some of the work that I'll be presenting here will be from what I did during my PhD. So because we have a diverse audience here, I'm just going to start off with some introductions of what we're doing. So just to give you a little bit of background, supplementary cementitious. So these are typically used to replace about 5 to 70% of the Portland cement in concrete, depending on what material you use, what its reactivity is, etc. And throughout the presentations in Asia, you would have seen that SCMs can be used to improve the concrete sustainability by way of reducing CO2 emissions, by reducing the amount of cement used, and durability by improving the long-term properties of concrete, right? And these SCMs are typically byproducts and waste products from other industries. So you have your fly ashes, you have your slag, you have silica fume and other materials. And these are typically composed of amorphous calcium aluminosilicate phases, emphasis on amorphous, and these can be classified into latent hydraulic, pozzolanic or inert materials. So latent hydraulic materials generally get activated once they generally react with water once they get activated. Pozzolanic materials require calcium hydroxide and water to react, and inert materials do not react in a pozzolanic or a latent hydraulic way, but they have other benefits in your concrete mixture. So just to give you a general idea of the reaction. So if you look at the figure that's placed right here, it's just cement and water that reacts to produce CSH or calcium silicate hydrate, and in the presence of SCMs, the calcium hydroxide that is formed along with the calcium silicate hydrate reacts to produce additional CSH, which densifies the microstructures and provides the benefits. So how do we know whether a material is reactive or not, and how do we know how much to use, right? So for this, in the US and elsewhere in the world, there have been a number of reactivity tests that have been created, and in essence, all these reactivity tests do a few things. So you basically have an environment with calcium hydroxide, supplementary cementitious materials, and an alkaline solution, and they're allowed to react, and you measure one or more of these parameters that are listed here. So you either measure the dissolution of the material, you measure the heat release, the bound water, calcium hydroxide consumption, or the strength. Okay? So for all of these methods that we have listed out here, you can either vary the mixture proportions, the solution composition, the testing temperature, or the pH of the environment in which the reaction happens. Okay? So we use different reactivity tests, and the most common one of those is the strength activity index test listed by ASTM C311. This is typically used in the US, and you also have lime consumption test, Chappell-Fratini, and also a modified lime strength test based on Canadian standards. There are two tests that I would focus on which have been gaining prominence in the recent years, which is the R3 test, which has been standardized in C1897, and its variant called the modified R3 test or the pozzolanic reactivity test, depending on which group you talk to. So, to give you an idea of what the modified R3 test is, it's basically just a small variant of an R3 test where you have calcium hydroxide and supplementary cementitious materials reacting in a ratio of 3:1 by mass, and you have a liquid to solid ratio of 0.9, and you have the reaction happening at a pH of 13.5, which has been supplied by a 0.5 molar potassium hydroxide solution in there. You carry out isothermal calorimetry at elevated temperature of 50 degrees Celsius for 10 days. This has been further shortened 3 days at the end of my PhD based on some of the results that I obtained. And you also carry out thermogravimetric analysis in case you want to classify the SCM into whether it is inert, latent hydraulic or pozzolanic. So if you just use the heat release values, you can tell whether an SCM is reactive or not. So we have a reactivity threshold which I'll talk about shortly. And the calcium hydroxide consumption together with your heat release values from isothermal calorimetry can give you the classification of the SCM. So what do these outputs mean? Like, what do all these points mean, right? So basically, let's say you have a plot of heat release versus calcium hydroxide consumption on the x-axis. Now, basically, the more reactive SCMs that you see there lie farther away from the origin. And you can distinguish between pozzolanic and latent hydraulic behavior and less reactive and more reactive behavior. So as you move from the origin, away from the origin, you see that there is increasing reactivity. And as you move from the right to left of this plot, you see that the behavior of the material changes from pozzolanic to latent hydraulic. As in, a material that consumes calcium hydroxide is more pozzolanic, just to reiterate again. And a material that needs an activator and can react with water on its own is latent hydraulic. So as you move from right to left of this plot, you see that the behavior changes from pozzolanic to latent hydraulic. So some of the later testing during my PhD ended up showing that there is a reactivity threshold of about 100 joules. So basically when you run the calorimetry, you end up, let's say you cross 100 joule threshold, you end up calling the material reactive. So the degree of reactivity varies based on other parameters, which we can talk about later. So in this particular work, as my title says, I evaluated a number of alternative SCMs. So the motivation for this is that our fly ash supplies are dwindling, your thermal power plants are getting shut down. You have a lot of clays, which is one source, which is an alternative SCM source. You have other sources of SCM, such as steel slags, etc. So we wanted to systematically see what all these SCMs or alternative sources of SCMs can do. So we had a bunch of slags, steel slags basically. We had the basic oxygen furnace slag, the ladle furnace slag. We also had pig iron cupola slags and copper slags. So I have to thank the MIT Sustainability Hub Elsa Olivetti for supplying these materials at some point. During my PhD. Then we have pozzolans. So we had corn ashes, rice husk ashes, a bunch of biomass ashes, ground lightweight aggregates. We also had glass powders, bottom ashes, and some natural pozzolans. So for some inert fillers, we had municipal solid waste incineration fly ash. Some work is being done by other professors also on this. We use basalt fines. I'll also talk about this a little bit. Sandstone fillers, some granite fillers, silica flour, and limestone. And I also studied some mine tailings as a part of this work. So just to dive into the results. So I'm just giving you the alternative SCM's reactivity. So the classification you see here in this plot has since been discarded, and we've actually gone to a more threshold based thing. So as we all know, reactivity is a continuous gradation. So we cannot actually separate them out into boundaries like these at this point. I'm just using an old plot. So from this plot, what we can see is that the alternative slags are generally inert or less reactive, and the alternative pozzolans show a wide range of reactivities based on what the material is and based on how the material was processed and what the source of the material was. And alternative fillers are, as expected, inert, and the D50 of these materials, or the median particle size of all these materials, varied from somewhere around 45 micron to around 75 micron, but most materials generally had a D50 of less than 75 micron. To go deeper into what the reactivity of alternate slags is, so if you look at this grayed out part on top, that's basically your ground granulated blast furnace slag, or the slag that we are traditionally used to, and we tested about 15 or 20 of those, and that's basically just shown in that region. So as you can see, they are well clustered. You have an average point that is shown by the blue marker there. But the alternative steel slags actually kind of exhibit an interesting behavior, that if you see the ladle furnace slag, it is generally inert, as you can see from the circles in the inert region and the latent hydraulic region. So one of the SCMs that you see there, which is basically somewhere around 500 joules of heat, that's basically an SCM that had meionite, which is a calcium aluminate phase that ended up causing high heat release. And when these are used in cement pastes, you observe sulfate imbalance, and you also observe low strengths in concretes. So then basic oxygen furnace slag is also less reactive, and its reactivity is from phases such as C3S and B-light. And a major concern here is the presence of free lime and magnesium oxide. And if you look at copper slags, they are crystalline and generally inert, and the pig iron slags are somewhat reactive but very less. The important thing about this is they have low calcium oxide contents. So that basically indicates that there could be some beneficiation that could be done for this, and you could do methods such as calcining that has been done in literature to improve its reactivity. So there are a bunch of treatment methods that are being done for this. So mechanochemical activation. So Pranoy and his students are continuing this work. And you can basically grind it further finer, you can separate the particles, you can remove some phases by heat stewing or heat treatment, and etc. So that's pretty much what has been done in terms of the activity of alternative slag. So moving on to alternative pozzolans. So generally, our pozzolan has been traditionally fly ash. So if you look at the grayed out region there, that generally gives you an idea of where the fly ash reactivity lies. We tested about 50 or 60 fly ashes in that region. And we see for the alternative pozzolans that the reactivity is generally comparable to fly ashes, or they have better reactivity than fly ashes depending on how they were processed. So for the biomass ashes shown by the blue triangles, they have a range of reactivities, and the reactivities depend on what the particle sizes are, how they were pre-treated or whether they were pre-treated, and the amount of unburned carbon or the loss and ignition of these materials. Some issues that we saw with biomass which need to be beneficiated are basically the high phosphorus pentoxide content, which basically retard your cement setting, and you have high alkali content in the system. The bottom ashes generally have low reactivity compared to fly ash, but when we ground the bottom ash, we actually improve reactivity significantly, as you can see from the dark green hollow circle. So some work has been done on this at Penn State, and they are still continuing the work. And as you can see, glass powders are generally pozzolanic, and grinding them improve the reactivity. I'll be talking about how we process this further in a couple of slides. And these glass powders need to be very carefully chosen, like the replacement levels have to be chosen based on its composition, because its composition is highly variable, the amount of replacement that you do could affect its ability to mitigate alkali-silica reaction or ASR. Some of the beneficiation methods that we tried out, it's a part of a couple of publications that I did during my PhD. We used acid washing, water washing, etc. to sort of get rid of the alkali. You can grind it finer to improve its reactivity, or ignite it to get rid of the unburned carbon and get the final low LOI ashes. Moving on to alternative fillers, they are generally inert, but they have secondary benefits, such as limestone. When you add it with any high aluminate SCMs, you end up having synergies. So a well-known example is limestone calcined clay cement. And the MSW ash is generally unreactive, but you can improve the reactivity of this. The problem is, this is quite complex. I'll refer back to one of the talks that a professor from UIUC, Nishant, gave a couple of conventions ago, that he compared MSW ash to Cthulhu at some point. So it's very complex because it contains fluoride, metallic aluminum, and heavy metals, and it becomes very difficult to sort of improve its reactivity. But it's possible. So basalt fines are inert ashes, and one of the PhD students of Pranoy is actually doing high temperature activation, and there has also been some work on grinding it finer and mechaноchemically activating it. So this is a work that is in progress right now. Now moving on. So I kept talking about beneficiation, etc. So for a couple of the SCMs that we have spoken about here, we ended up trying to grind it finer to see what effects it had on its properties. So basically, we improved the SCM fineness to see how it affected the reactivity and the paste property. So as you can see here, I have two supplementary cementitious materials and an inert filler. So limestone is the inert filler, and then I have a pumice, which is a natural pozzolan, an alternative source, and I have a glass powder that has been ground to 3 different fineness. Okay. For cementitious paste testing, we ended up replacing 30% of the cement by mass with supplementary cementitious materials at a water-to-cementitious materials ratio of 0.40. And we also wanted to see if fineness impact is similar for different materials and different properties. So if you look at the two plots up here, these are the modified R3 test outputs. So as you can see, with an increase in particle sizes, we see that there is a clear decrease in reactivity for the reactive SCMs. Now, if you take the black dots down there, the black squares, these are limestone. We see that limestone fineness does not affect its reactivity, and it just stays as a filler in the system. So, just to give you sort of a summary of the slide, for pozzolanic SCMs, reactivity generally increases with fineness, and there is no impact for inert limestone. Funnily enough, the materials that we had here for pumice and glass powder had very similar slope values, so we thought of just clubbing them up, and that's why you see the green line up there. Moving on to cementitious paste testing. So, like I said, we replaced 30% of the cement by mass with supplementary cementitious materials. I realize it's done by volume, but it was done by mass. So, SCM fineness and paste heat. So, if you look at the plot on your left, it's basically the response, basically the heat flow at every instant, and the plot on the right gives you the 7-day heat release values or the cumulative values. So basically the takeaways from these plots are that with increase in fineness or with increase in median particle sizes, or rather the decrease in median particle sizes, we see that the peak heat flow values and the heat release values increases, and at early ages all these SCMs provide a filler effect, which basically or acts as nucleation sites, which basically increases the heat flow there. And for coarser SCMs, we see that the effect is one of pure dilution. As you can see, we replace 30% of the material with or 30% of the cement with fly ash or any of these materials basically. So you see that the 30% dilution line that we show there is basically a 2-0 case where if you replace it by 30%, it's supposed to basically decrease the properties by 30%, but in reality that's not going to be the case. But for coarser SCMs, we see that the effect is one of pure dilution, and limestone clearly has a different level of filler effect, as you can see from the slope on the two plots. So basically the black dotted line that you see is for limestones, and they have a clearly different level of filler effect. So as the fineness increases, its reactivity exponentially increases, or rather its effect on cement paste heat exponentially increases. Looking at paste calcium hydroxide, at early ages, we saw that filler effect causes slightly higher calcium hydroxide content at 7 days than expected from dilution for all materials. And evidence of reactive SCMs is basically seen at later ages, where you see that a higher fineness material is more pozzolanically reactive and more calcium hydroxide has been consumed compared to an inert material like limestone, where it basically has a negative slope, which basically means that it's inert and it's just staying in the system without any reactions. Moving on to paste compressive strength, which is always our favorite test, right? So what we see is that dilution dominates at early ages, if you can look at the plot on your left, and some effect of fineness is also seen, especially for the case of limestone and between very coarse and very fine SCMs here. As always with the case of SCMs, very strong effects of fineness and reactivity are seen at later ages. The coarser SCMs largely show just pure dilution, as you can see from the plot on your right, especially with the glass powder represented by the blue triangle. And finer SCMs show some reaction, and for inert limestone, there has been no reaction beyond the early age effect, and it just remains fairly at dilution levels. Moving on to transport properties, which is measured by cementitious paste bulk resistivity. We saw that at early ages there was no SCM effect on bulk resistivity. However, we saw clear differences between reactive and non-reactive SCMs at 56 days, which is basically what you see at the plot to the right. So the reasons for this could be pore refinement, the effect of pore solution, and the alkali binding because of supplementary cementitious materials present in the system, and so on. At very low fineness levels, again as you can see at the far end of the plot at 120 median particle size, you'll see that the reactive SCMs can appear inert. So just correlating modified R3 test and the paste properties, we saw that there was strong correlations between the 1-day heat release in the modified R3 test with a 56-day calcium hydroxide content, compressive strength, and bulk resistivity. And this is basically saying that modified R3 test can predict later age cementitious paste behavior and post-concrete behavior. And based on this, we ended up doing a bunch of other tests, studying the kinetic effects, etc. And then we ended up shortening the modified R3 test duration to 3 days. So just to conclude my talk, reactivity tests alone cannot be used for assessing SCMs, as you saw from the case of alternative SCMs. You need a full material classification, you need to understand what phases are present, you need to understand the chemical composition, you need to understand its fineness, and there is a marked increase in SCM reactivity based on the modified R3 test. Higher the fineness, higher was the reactivity for the materials. For basically different ages, different effects were seen. So filler effects were seen at early ages for most SCMs, whereas for reactive SCMs you saw the pozzolanic effects. And beneficiation using various methods can be carried out to improve the reactivity. So one example was shown here for grinding. This is a very promising area that is being currently explored by the research group at University of Miami. So thank you, and if you have any questions, I'm happy to take them now.